Good evening, students. I'll start with the class. Today we'll start with a new chapter, which is thermal properties of matter. I'll just change the marker. Okay, from the word thermal, this word you all must have heard from the word thermometer. Thermometer. Whenever you get fever and all, we always check a fever with the help of a thermometer. So the word thermometer is related to thermal, means something related to heat. Okay, so what is this heat? Heat is nothing but kind of form of energy, some kind of energy. We have light energy. Okay, same way we have heat energy, various types of energies, chemical energy, light energy, kinetic energy. There is even heat is one form of energy. So how is this heat generated normally? Consider you have some body, anything, any material or anything. Okay, there will be always any substance is made up of many molecules or atoms. So there will be many molecules tightly packed or closely, whichever. So suppose if these are the molecules. Okay, suppose if it gets any, suppose if you are providing any fire or any kind of external, suppose anything is happening, or sometimes within internal also, what is going to happen is if a fire is provided here. Okay, so what happens, these molecules start gaining energy from here. So the moment they get energy, they start moving. Okay, these molecules start moving amongst each other. Depends how fast they move. Some of them move very fast, some of the substances they might move very slowly. So when they start moving, they collide with each other. Okay, like this one will go and hit this one will go and hit this one. So whenever all the molecules, okay, they hit among each other or they collide each other, what is going to happen is there is a friction. Same thing, when you try to rub your hands, what is going to happen? There is heat generated between your hands. Why? There is some kind of friction, there is some movement. Okay, there is some collision. So same way, when these molecules collide with each other, there is always a friction, and because of that, there is heat generated by movement of the molecules or collision of molecules. Okay, it means it's the energy released out of friction, so that is the heat. Now suppose if you have a cold body or hot body. Okay, hot, and this is suppose a cold. Okay, now this what is happening, suppose any time it will always move from the higher to the lower. So it would be what, like anything, the heat would get transferred from here to here. Like if you keep a cup of tea, suppose, okay, hot cup of tea. Now what is going to happen? This will become cold after some time. Why? Because this is hot, but comparatively this outside it is cold. Compared to this is as a lower temperature, and this has a higher temperature. So all the heat from here will move out. Okay, till it becomes at equilibrium. Equilibrium means the same temperature as that of the room temperature. So this is what happens. The heat is nothing but like a transfer of energy, okay, from one state to another state. I'll give you the definition of heat. Before that, I'll just tell you one more thing. Now heat, what is it? How is it measured? Since it is the form of energy, okay, it is always measured in terms of joules because it is energy. Now you will say work. is also kind of energy. Work is also in terms of joules. So is work equals to heat? Both are energies, but only thing the way of writing, they are different forms. Okay, so work is nothing but kind of mechanical form of energy. Like when you actually do some mechanical work, like riding a cycle, okay, or running, so that is mechanical form. When you're doing some mechanical thing, the energy required is called work. But if it is within the molecules and all non-mechanical way, then it is heat. This is the difference between work and heat. Both are energies only, but this is in the form of mechanical, this is non-mechanical. Just for your information, no one will ask you for exam, but just to know the difference. So heat is nothing but the energy only. Now you can write what this heat is: form of energy transferred between two or more systems. How I told you, no, if there are two boxes, it can take place here also. If there is one more box, it can take place here also. Between two or more systems and its surrounding due to temperature difference. Due to the temperature difference. Why is it moving from one place to another? The cup of tea, here it is higher temperature, here it is lower temperature, so there is a difference. So this moves till they become equal. Okay, so whenever there is a difference in temperature, always there will be transfer of heat taking place, either okay more from higher to the lower one. So this is heat. You can write it is unit is joules for heat. That's SI unit. Next is what is temperature. Whenever you say I've got fever, means your temperature of the body has increased. So what it means is your body inside, like all the virus, this your antibodies, there are something called as antibodies inside the body. So they try to fight against the virus. So this whatever when you're fighting against it, there is a movement of these molecules. Like the movement of antibodies cause heat generation inside your body. So that heat, okay, makes your body temperature rise. So it's nothing but like average heat, overall like average heat of any body. Overall and average heat of the body, if you want to know, then it is measured and can be measured in terms of temperature. Or you can say temperature, it indicates or in technical terms you can write it is a relative measure of hotness or coldness. It is a relative measure of hotness or coldness of any object. Now you can measure temperature in three various ways. Okay, the device used to measure temperature is usually device used is thermometer. Usually we have seen the liquid filled is the liquid one, that is mercury. Okay, or sometimes there's special kind of alcohol also. Usually we use this. Okay, so liquid filled, like the liquid which is there in the thermometer is mercury. Now there are three ways we can represent the temperature. Whenever you check your fever, okay, so it could be you never check in terms of degree Celsius. Whenever you say 100, your fever, if you say 100 degrees Celsius, I got 100 fever degree Celsius, then it would be like you would be boiling like water. That's the boiling point of water. So whenever we say 100, it's not Celsius, it's Fahrenheit. Okay, we'll understand that. So there are three ways of representing a body this or any temperature. One is degree Celsius, Kelvin, that is K, and the other one is Fahrenheit. H is silent, Fahrenheit. That is F. Degree Fahrenheit is the normal. And this is straight away Kelvin. Yeah. So these are the three ways you can represent a temperature. So whenever you measure any temperature, there are something called as two fixed points. Now later we have to know what is the relation between them. So before that, you have to know there are something called as two fixed points of any temperature. The two fixed points are, one is ice point, also called as the freezing point. The other one is steam point, called as the boiling point. Okay. See, best example to remember is water. Now water can be in three states. One is solid, liquid, and gas. So whenever it's in the liquid form, what you do, if you try to heat it, okay, keep on increasing its temperature, keep on giving energy to it, at some point it will start boiling. The moment it start boiling, the liquid will convert into gas. That the boiling point will be the last boiling point. So the moment it reaches 100 degree, it will convert into steam. So that is one point where liquid can go into water, can go into steam. And the other way around is if you try to decrease the temperature, if you try to freeze the water, at some point it will become ice. Okay, so the 2 points. So this is with reference to water. Okay, with reference to pure water. So whatever will be deriving the relation, that is with reference to pure water. So what will be the ice point? This will be 0 degree Celsius for water, and this is 100 degrees Celsius. Okay. Now we'll see what happens to the Kelvin and the Fahrenheit. So I can want you can take a screenshot and see if you are not able to write it quickly, or it's there in the notes also which I've given. You just go through it, you read it, you will understand. Now we'll try to derive the relationship. Derive means exam, derivation is not asked. Only the formula is you have to know the relation. But I'll tell you how you get the relation between all these three things. First you can consider these are your steam points. This is the ice point. This is for degree Celsius. This is for degree, sorry, this is for degree Fahrenheit I'll give. And this is for Kelvin. In terms of degree, I told you the ice point is 0 degree Celsius. This is 100 degrees Celsius. Okay. The ice point and steam point is 0 degree and 100 degree. In terms of Fahrenheit, it is this you have to remember 32 degree Fahrenheit. This is Celsius, and this is 212. You have to write this also. And in terms of Kelvin, it is 273.15 Kelvin. And the other one is, there is no degree, 373.15 Kelvin. All these three things you should know. One is in terms of Celsius, Fahrenheit, and Kelvin, the ice point and the steam point. So now I'll try to derive the relation between them. So let us plot a graph for this. We'll try to see what is the relation between Celsius and Fahrenheit. So what I'll do, I'll put temperature in terms of Celsius in here. This is temperature. In terms of degree Celsius, I'll put on the x-axis, and temperature in terms of degree Fahrenheit, I'll put on the y-axis. Okay. So temperature in terms of degree, what is the ice point? Starting is 0. And then steam point, it will go on increasing 10, 20, 30, 40 like that. How much is the steam point? 100. So this will be 100 degrees Celsius. This right here. So this is my temperature in terms of, I just write it shortcut, in terms of degree Celsius. So this I plotted here on the x-axis. Now Fahrenheit I want to plot on the y-axis. So first, what is that? On the y-axis I have to mark. Starting ice point is where? 32. This is not 32. So if you would count, it would be like 10, 20, 30, maybe here somewhere. Since we are not writing the scale, approximately 30 would be around here, like 10, 20, 30 up. You cannot put 32 here at 0 origin. Somewhere up, some. So this I'll take it as 32 degree. And then steam point is somewhere here. 2, 1, 2 like that. 40, 50, 60 like that. It will go up till 200. Okay. So I'll try to find a relation. This is maximum here. Whenever this is 100, okay, what is this? 212. In terms of Celsius, if it is 100, then in terms of Fahrenheit, it is 212, this point. When it is 0, this is 32 here. And this I'm comparing. 0 and 32. I'll just join this because this is your steam, this is what your ice point, and this is your steam. Okay, ice point and the steam. So I just related them. This is the relation, the graph between this and this. It's there in your textbook also, same graph. So I'll just draw like this. Now randomly, suppose I want to know, I take any, now this is 0, this is 100. I suppose I've checked, I put thermometer and I've checked of some body, okay, somewhere this answer I get, suppose 50 or whatever it may be, we don't know. This, let it be like TC, temperature in terms of Celsius, I'm getting this. Now I want to know in terms of Fahrenheit, how much it would be in terms of Fahrenheit. So how to check? Just extend the line, okay. So this would be in terms of your Fahrenheit. This will be a TF. Whatever is in terms of degree on the x-axis, it will be Fahrenheit on the y-axis. Same here. This, and it would be like. So I'll just name these letters A, B, and C, and this I'll keep it as B dash, C dash. The bigger triangle, I'll mark it as A, B, C. The smaller one, I'll make it as B dash, C dash. If you look at this triangle, one smaller triangle is inside a bigger triangle. So they are called as similar triangles. In 10th standard, you all must have studied. Triangle A, B dash, C dash is similar to triangle ABC. So for similar, you know that smaller side upon bigger side, that is B dash upon BC, is always equals to this upon the bigger one, AC dash upon AC. No need to by heart this derivation, just try to understand it. No one will ask you to derive it. So what is this? Only the formula last what we will get, no, that you have to remember. Now B dash C dash is how much? This much distance, this length, no? How much is this length from here to here? This full TF minus 32 if you do, then you will get this length. What is B dash C dash? The whole thing, this full thing minus this small thing, then you will get this length. So it is nothing but TF minus 32 upon what is BC? This whole length, this much. How much it is? 212 minus 32. BC is how much? This full length minus 32. I want this much distance, BC. So full thing minus this 32. And then AC dash 0 to TC minus 0. This one from here to here. And then full thing 100 minus 0. AC is this 0 to 100. That will be straight away 100. Now basically this relation you have to remember this formula. TF minus 32 upon 180 is equals to TC upon 100. This is the relation between Fahrenheit and degree Celsius. Same way, just before putting in the box, in term like that only, since we don't have it for exam, same logic you can try with Kelvin. So directly I'll give you the answer for Kelvin. Kelvin, it would have been same logic here. So K minus 273.15 upon 373. This points you could have put. This would be 273. This would have been 373. So if you do this, finally writing the answer. So this is the relation between all the three scales. If answer is given in terms of degree Celsius and you want in Kelvin, equate these two equations, put the value, calculate the value of K. If these two are given, then you can take this equation. One example I'll solve. So just remember this formula. If temperature in terms of degree Celsius is 50 degrees Celsius, find TF. Temperature in terms of Fahrenheit. I want to convert degree Celsius into Fahrenheit basically. Find means you have to convert this into Fahrenheit. So which two are needed now? This first two. So use the formula TF minus 32 upon 180. Some of the teachers will simplify this also and write a cancel and then write a shortcut. TC is 50 upon 100. This will go up. Is 90 degrees. Then TF would be 90 plus 32, 122 Fahrenheit. So 50 degrees Celsius is equals to 122 Fahrenheit. Now, suppose if I say I had 102 degree Fahrenheit fever. Now let us consider your temperature was second one. Suppose 102 degree. So whenever now remember, somebody asks you of fever, if you have 102, it's not degrees Celsius, it's Fahrenheit. So if you want to tell the person in terms of degrees, then you use the formula and convert and see how much degree fever you would have. 102. Same equation. Now put TF here and calculate TC. So minus it. that would be 70. This would come up. This you can do. 2 9s are 5s are. Okay, then you can divide 350 by 9. 9 3s are 27. Okay, 9 9s are 81. 9 7s are 9 8s are 72. Then it would go on increase. So around 30 it would go on. So 38.9 degrees Celsius would be your temperature. If you 100 and we have 102 Fahrenheit fever, it means in terms of degrees it is 38.9 degrees Celsius. So this is how you can convert any temperature from one form into another using that formula, that relation you have to remember. Now sometimes thermometers can have gas filled also. How you have mercury, no, like that you can have gas filled. We'll see what is the ideal gas equation. Okay, any thermometer, no, suppose if you have gas filled inside it, what is going to happen? Gas you cannot simply keep. Even in the cylinder, when you have a gas, okay, that is kept under pressure, because otherwise it would normally escape. So what happens is it's always in the compressed form. There's always a pressure put inside and try to fill. Otherwise, very little gas will get filled up. Like how if you would fill like a balloon with air, okay, a balloon would have very less air. If that much only a cylinder was filled up with that much air, how much you would fill in the balloon, it would get over in a day only or within an hour. Whenever they put any gas, they always put it under pressure. Okay, so there is always a pressure, and this whatever is filled up will always have volume also. How much volume has been compressed to, how much space it is filled up. Okay, so based on that, okay, suppose if you have an ideal gas equation, they have already, it's a derived one. You don't have to derive it, just have to remember the equation to ask. This is the relation, or T you can take it up. PV is mu R and T. This mu is a constant. P is the pressure. V is volume. T is the temperature. And mu is nothing but your universal gas constant. This is your universal gas constant. Mu is number of moles in the sample of gas. and R is universal gas constant. The value is fixed for the constant. R value is 8.3 joules per mole per Kelvin. This much we remember, 8.31. So it's a fixed value. So this is ideal gas equation for any thermometer filled with a gas. If you see pressure, these are both constant. These are constant. So PV is directly dependent on your temperature. Now for constant volume thermometer, for a constant volume. Now what is happening? You are keeping it constant. Constant means same, not changing. Okay. Suppose if you are keeping this constant, this is not going to change. Then what will happen? Pressure will be only dependent on the temperature, because this is not going to change at all. If you're keeping the volume of the thermometer same without any difference, only thing the gas pressure, whether it will expand or this gas, that will be dependent on the temperature. Same like mercury, no? When you have inside the mercury, what is happening? When it uh, finds any heat, as your body heat rises, the mercury expands. Okay, so same way, suppose if your temperature is increasing, then your pressure also will increase of the gas. Suppose if it is decreasing, then this also would decrease. So it is basically temperature and pressure is dependent, and that's how you can measure your fever or any temperature, because volume anyways we are keeping same. Okay, for constant volume thermometer, P will be directly proportional to T. Okay. Now, next one is based on this only. What is absolute temperature? We'll see. We'll try to plot one graph. If this is temperature, this is pressure. All these graphs are there in the notes also. Now, what I have told you, suppose I'm at 100 degrees, suppose I'm starting from here. Suppose. Now, what I'll do, I'm trying to reduce the temperature. Since they are directly proportional, what is going to happen if I'm trying to reduce the temperature, pressure will also reduce. Okay. As I keep on decreasing the temperature, pressure will also keep on decreasing. So it will look like, okay, finally at some point it would go zero. So the point which it goes zero, the pressure becomes zero. As you go on reducing the temperature, at this point, the temperature is, they have calculated, okay, based on the experiments, it is 27 minus 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . 273.15. . This is normal 0 degree. Okay. This at here the pressure is 0 at this point. An object is taken while conducting the experiment. Suppose from 100 of the thermometer, on the thermometer it is checked. Suppose if this was kept under some boiling water and on the thermometer. Now what has happened? First it was at 100, then they went on reducing it. So what happened? The pressure also went on reducing. Okay. Then they calculated, they plotted the points. At what point, at what temperature they went on reducing till in negative temperature. We reached at 0, still the pressure was not 0. Still they further reduced the temperature, like in the freezing point and about less than that. And then finally at this particular temperature, the pressure of the thermometer went 0. So this point is called as absolute temperature, or also called as absolute zero. Let's write here. So under the graph, we can write absolute zero. So what is absolute zero? When temperature is reduced, pressure reduces. When pressure becomes, then pressure becomes zero. At minus 27, therefore the absolute zero is degrees Celsius. Absolute zero means when the pressure is zero, what is the temperature? Reduced, also we use the word decreased. Huh? When the temperature is decreased, pressure decreases. That word also you can. So just draw the diagram that again and keep. We had written the steam point this now. So again we'll just write it again. This was steam point. This was boiling point. Now we'll write absolute zero also. One more we'll add. You can go back or you can draw it again also. For degree Celsius, this will be for degree Fahrenheit. And this will be for Kelvin. For degree Celsius, we just now saw that is minus 273.15. This was 0 degree Celsius and this was 100 degrees. Fahrenheit, what it was? 32. This was 212. This we are only this part. Now we are just adding this for everyone. In terms of Fahrenheit, absolute zero will be, this is in terms of Celsius. In terms of Fahrenheit, it is minus 459.69. And in terms of Kelvin, this is zero. Oh, it's not okay, huh? 0 Kelvin. Why it is called absolute zero? Because this is zero with respect to Kelvin. So that's why it is also called, represented, also said as Kelvin temperature, because it was named after that British scientist Lord Kelvin, because it is zero. So this is for Kelvin temperature scale. You can, this is in terms of degree Celsius. Huh? For zero it is Kelvin. So this was about the different ways of writing the temperatures. One more graph, if you see, it's there in the notes, just check on it. If you have many gases, okay, gas A, suppose if you have any gas B, whichever point you may start, what is going to happen is, if you reduce this is pressure, same. Okay, whichever gas you try, normally temperature, when you decrease their pressure, finally they will all go to the same zero. Any gas you this reduce its temperature, finally the pressure would become zero at the same point. These are all low density gases. Low density means very light gases, not the heavy gases, light one. They've tried experimenting 3 different gases. They reduce the pressure. Finally, they have the same gas A, B, C have same absolute zero. That is minus 2763.15. No matter where they start from, finally they end up at the same zero. Next topic is thermal expansion. So whenever you heat anything, most of the substances, heat means, now consider thermometer only. Inside that mercury is there. Suppose if you are giving it, if you keep it in the water and start boiling the water, slowly the mercury will rise. Means what? Something is happening to that liquid. Either it's expanding. Okay, that's why it is going up. So there are some changes which happen whenever you heat it, or sometimes if you are cooling something. Okay, so it might contract, it might expand based on the properties of the which object. Some may expand based on heating, some may contract based on heating. Okay. So what happens is, suppose if you are changing the temperature, means basically if you are heating it or cooling it, heating or cooling the substance, it can cause a change in its dimensions. Dimensions means can either increase its length and all. So this increase, if it is increasing, then it is called expansion. Okay. If it's decreasing, then it's called contraction. But anyways, we are studying the topic thermal expansion. So we'll be talking about the substances which will expand on heating or cooling. Due to increase in the temperature, if the temperature increases, the length or the volume of the substance will increase. And this is called as thermal expansion. Increase in temperature is called thermal expansion. So there are three types of thermal expansion. One is linear. Here length increases, linear expansion. Next is area expansion. From the word only, linear means length, area expansion will be area increases. The third one is volume expansion, volume increase. Okay, so increase in the length is called as linear expansion, increase in the area is called as area expansion, and increase in the volume is called as volume expansion. And under that, you can just draw the diagram and show. If this is your original length, suppose if the length is increasing, this is the delta L, change in the length from the original, then this is for linear. Area, it could be square, it could be rectangle, anything. This inside is your original length and the breadth would increase. So overall the area is increasing. I have shaded the increased region. And for volume, let's just draw the outline. Suppose overall the volume increases, then this is volume expansion, delta V, change in the volume. This is all happening when you increase the temperature of that particular object. So first we'll see what is happening for the linear relation. We'll try to find out in detail. So for linear expansion, if temperature changes, length changes. So this change in the length, no? This fractional change in length is proportional to change in temperature. Obviously, only if the temperature changes, the length will change. So length is dependent on the temperature. There is no change in the temperature, length will not at all change. Okay, so this delta L upon L is dependent on the change in the temperature. Fractional means like this, delta L upon L is dependent on the temperature change. So whenever we remove this direct proportionality sign, when we represent it by a equal sign, we always put some constant. That this is direct proportional sign, no? And this what I'm representing is alpha. This and this is not same. Can represent like this alpha. Since it is linear expansion, the constant which I'll use is L. How we put K, no? Whenever we remove this, we normally put K constant. But for linear expansion, we'll use the letter alpha, L. This and this is not same. This is proportionality sign and this is alpha. This is to be read as alpha. Your teacher might use some other letter, gamma also, anything. Okay, so this is the relation for this. So what is this? Alpha L is called coefficient of linear expansion. It is constant. Just circle this in. Depends on material of the rod. So different rods will have different values, but it does not change. Even if you are increasing the temperature of that particular, suppose there's a rod, okay, you are giving it heat, but this alpha will not change, it will remain constant. But different rods, suppose this is a steel rod, this might have different value. This is aluminum rod might have different value. So the table is already there in the notes. If the words are not clear, no, which the Xerox which I gave, just refer your textbook. It's there in the textbook also. Aluminum, there are some different values which are given for different materials. Okay, for aluminum, then brass, iron, copper, silver, gold, glass, and lead. Okay, so one table has been given. So different things have been given. Aluminum, and then these values, how much is this? So 2.5, 1.8, like that for different materials have been given. So this is for linear expansion. The same way we'll see what is we'll check what is area expansion. Area expansion is as temperature increases, area changes. So change in area depends on or directly proportional. Depends means directly proportional on temperature. Or you can say fractional change. Fractional change in the area depends on change in temperature. Same like the previous one, only the letters used will be A now instead of L. We will remove the sign. Now alpha instead of L it will be A now. Where alpha A is coefficient of area expansion. And the third one is volume expansion. Here this you can also write as this equation, no? You can write it as this way also. A you can take this side, huh? For L also you can write the same. You can write this side also. A you can always take. Same way delta L upon L, L you can always take on the other side. This or this, both mean both are correct. You can write like this or like this. So same thing, volume, fractional directly I write. Or as temperature increases, volume increases. Therefore, fractional change in volume depends on fractional change in temperature. Or directly, sorry, depends on change in temperature, not fractional. So this will be delta V upon V is directly proportional to delta T. This is fractional, this is normal. Now when you remove, now this will be alpha V instead of A now. This is for volume, so this will be alpha V. Where alpha V is coefficient of volume expansion. Here, this important thing to know is this fellow is not constant. You can say not strictly constant. Why I will say is, I'll give this explanation. For gases at low temperature, alpha V changes for alpha V changes with temperature. that is alpha V is dependent on the temperature. It is not constant. How I told no, for linear and all, even if you give fire, if you keep heating no, the value, suppose what was it, aluminum has how much, 2.5, alpha L is 2.5 for aluminum. So even if you keep on increasing the temperature, this 2.5 will always remain same. Whether the aluminum rod expands also, this will never change. But under volume expansion for some gases, no, suppose there is an expansion, this alpha V will not remain the same. This alpha V, as you increase the heat, this also will keep increasing or decreasing, depends. Okay, so this will be dependent on the temperature. So if you are increasing the temperature, this volume, this what is that, alpha V also will change at low temperature. But once like this is up till like 200, 300, or maybe up till 400, and after that at very high temperature, then it will not change, then it remains constant. So as from the graph I show you, suppose if you have a temperature in terms of Kelvin, and this is this alpha V, what will happen? This is up till suppose 250, this is 500, very high temperature. This is at low, this is low temperature, and we know that this part is high temperature. Now this alpha V, what is going to happen? Whenever it is at low temperature, no, it will keep on increasing. As you increase the temperature, alpha, alpha V will also increase, like this, something. And then once it reaches very high temperature, no, then it remains constant. Then it will not change. Okay, so it's approximately like this. Then it will always remain the same. Even if you increase the temperature, alpha V, suppose if it was 1.8, then it will remain 1.8. But at lower temperatures, as you increase the temperature, even alpha V is changing. It is increased. But after, at high temperature, alpha V is constant. Low temperature, it changes. At high temperature, it remains constant. This is only for volume expansion, okay, and for gases especially. Or even if some other substances also, like iron, you know. So this was about expansions, linear expansion. Area expansion and volume expansion. Just see what happens. Thermal expansion of water. Next topic. Suppose if you have this much water, like, okay, you are starting at 100 degrees, suppose it's boiling. Then you go on reducing the temperature, suppose. Now you keep reducing between 100 to till almost 4 degree. As you decrease the temperature, what is going to happen? The volume will keep on reducing. Okay, now we are trying to cool it. Contracts, okay, water will try to contract. Although I'm not showing a slightly, it's not like full, very small difference, but this contracts. So basically what it means is its volume of water reduces or decreases when we cool it. Okay, when we cool it from whichever 100 degree to or room temperature to 400 degrees Celsius. What is going to happen? Volume is going to slightly decrease. What is density formula? Density is nothing but mass upon volume. This is density. Mass is anyways remaining constant. That is not going to change. Okay, like it just tries the molecules gets compressed. That's the only thing. Contracts means the volume is decreasing. It's not evaporating and going, but only thing the molecules come closer. That it means. Okay. So volume is slightly decreasing means what is going to happen? The smaller quantity means density will increase because they are inversely proportional. If you are reducing this number means automatically numerator dividing by a smaller number means this is higher number. M divided by 2 and M divided by 10. If you increase the number, this quantity will reduce. But if you are decreasing the number, this quantity will increase. Okay. So now what happens? Volume reduces. Therefore, density is increasing. Means more dense it will become. The molecules will become dense. Dense means thick. Okay, this is up till 4 degree. Now, this is from 0 to 4, no? No. So here what is happening? Volume reduces, density increase. Now this is below 4. This is from 100 to 4. Now this is below 4. Here what is now going to happen? Again now volume will start increasing after 4 degree and density will decrease. So this was for from 100 to 4 degree. Now this is for below 4 degree. Below 4 degrees Celsius, volume of water increases. It's like we are trying to cool the water. Now the volume is starting to increase. If you have noticed, whenever you are keeping the bottle in the fridge, okay, so first anyways it will go on, volume will of the this will reduce for slightly till it reaches 4 degree. Okay, and now the moment it starts freezing, like it's starting to become like ice little bit lower than 4 degree, slowly the water in the bottle will start rising. So if you are keeping a glass bottle, softening bottle of glass in the deep freezer. Okay, once it starts going from below this, then slowly the volume of the water will start increasing. So the water is expanding, and therefore the density will increase. Density will decrease. It become light in weight. Ice is always light in weight. For density decreases. Now what is going to happen as you expand? That's why the bottle kept in the deep freeze, no, it will blast. If you keep it, no, glass bottle, soft drink bottle and all, why it blasts? Because the ice will expand slightly and it has no space. Suppose if it's a fully packed bottle and it has no space for the water to ice to expand, then the glass bottle will break. So that's why below degree the volume of the water increases and the density decreases. So if you want to represent in terms of graph, so from here 4 degree will be 100 and this is 0. You're starting from this point, suppose this is your density or volume. Volume may be somewhere here now. Now you are trying to reduce the temperature, you are trying to cool it down. So what did I tell you? The volume first decreases. Okay, from 100 to 4, volume decreases till this point. And after this point, what is going to happen? The volume starts increasing. This is for the ice part. The volume increase from here to keep it little bit higher like this. This of the water, huh? The volume decreases, density increases. Yeah, density decrease. This is there on the notes. If you see, this is the temperature versus volume for water expansion. Same thing is going to, we have temperature. This is was for volume, no, you'll not confuse. Temperature, and this is for density support. This is 5 and this may be 100. From here to here, density is increasing, no? Volume decreases, so density is increasing. This they given as 10. Maybe from 10 only they are calculating. At this point, it will reach 4 or maybe 5. Like reference they have taken as 5, but actually it is at 4. And then it will reduce. From here to here, density will reduce. Here to here, density will increase. Not 45. You can just refer it as 4. Here, density increases. Here, density decreases from 4 to 0. Okay, so this is called as thermal expansion behavior of water. So related to this only, last thing what I explain is, suppose for our ponds or lakes, water lakes, okay, what happens for water ponds or lakes? If you have lake, there is water, suppose it's very cold outside in cold regions and all. If you have noticed what is happening, all the fishes are still there inside, but this top cover is filled up with ice. Why there is no ice at the bottom? Okay, why is it always on top? What is going to happen is, why this happens? this same pond. Now this is very extremely cold here out. So this water starts getting little cold. Okay, till that, what is going to happen? This will, now it's cooling. Okay, this water is starting to cool. So this will contract little bit from 100. Suppose room temperature it was at 20. Now it is going suppose at like 4 degree towards this. This will start contracting. And this is called as dense. Forget about this contract. You can just say dense water, more dense water. And here it is less dense water. So what is going to happen? More dense water means little heavy. So more dense water will go down, and that little warm water, no, this is cold water. So that will try to come down, and less dense water will try to go up. So what happens? This less dense water means it will start floating. This less floats. So basically, it will go up, and like when the moment it becomes ice, no, so ice is less dense then. So ice will always float on the top, and then it gets covered up. The whole area when it gets covered up, the sunlight will stop, and this means this is like a insulator. So the ice will not form inside, it remains warm only. It's like one block will come on top, and that's why the fishes can grow inside. Okay, so basically what happens is starting the water is there normal temperature. When it's very cold outside, this will, the top layer will start becoming cold, so it will be slightly dense, so it will go down. The less dense comparatively will come up. This process will keep on happening till little bit of ice is formed. Okay, till it goes below 4 degrees Celsius, and after 4 degree then it will start slightly, and then 0, less than 0, it will completely turn into ice, then freeze, and ice is light in weight, so it will float. Okay, so this is the logic behind why the this, what is that, otherwise what would happen if entire thing had become ice? There would be no life under the pond or lake. So the explanation part is already there in the notes. Just check the page. Okay, this page it is on the notes. Yeah, this paragraph they have explained. You can write in your own words, or the same letters also you can copy. So I'll just read it out. It says, as the lake cools, no, towards 4 degree means what? From suppose 20 to 4 degree, water near the surface, it will lose energy. Means what? Heat will go out, cold will come in. This is like hot water, which is there compared to this external. So this energy is lost. So this water top layer will become slightly cold. So when it is becoming slightly cold, it will become heavy little bit, because I told you from 100 to 4 degree, the it becomes, volume decreases and density increases, and it basically it means contracts. So this density means heavy. Density increases and it becomes heavy. So this heavy water will go down, and then the warmer one, slightly warm one, which is there in the below, is less dense. It will come up. Okay, and this process continues till the surface it freezes, and then it remains freezed on top one. It never goes down back, because that is anyways less dense. Okay, so this is thermal expansion of water behavior. I'll stop here. Next class we'll derive the relations between the coefficients of volume and linear expansion.